Turn around as soon as possible.
Sat-nav lady, how much do we love her? Not.
No, you get the amazing technology behind the sat-nav lady, GPS. Up there. About 8,000 times a year, volunteer lifeboat crews like this one get sent out all around the waters of the UK and the Republic of Ireland to perform rescues. But each time they go out, they rely on one fact, that 12,000 miles that away, in what's called a mid-orbit, a 27 global positioning satellite. Okay. How much more difficult would your job be if you didn't have GPS?
With the GPS, you get a casualty called up, you've got their position straight away, put it into the satellite system, gives us range, bearing, distance to run, gets you to where you need to be straight away. Time is lives, absolutely vital to our saving work.
The American GPS satellites work alongside another Russian system called GLONASS. And to explain all, I'm meeting a GPS expert at a satellite tracking station in East Sussex.
How does it all work? When I punch in an address here and press go, what's going on?
So the first thing the device is doing, it's measuring the distance from here, from the receiver, out to those satellites. Second thing it's doing, it's tracking these signals broadcast by the satellite, which is telling the box where the satellites are up in space.
So this is just like a radio receiver, if you like, picking up sort of radio signals, but these radio signals have data in them coming from satellites.
Exactly, that's right. So the satellite spits out a little blob of electromagnetic energy, and on that is like a time mark. It says, OK, I transmitted this signal at this time. And then as well as transmitting the time, it says, roughly, this is where I was when I transmitted the signal.
So you've got a very, very accurate clock in there?
Very, very accurate clock, yeah. And the receiver down here has also got a clock in it.
Yeah.
So let's just take the phone here, for example, OK? So there's a clock in here, there's a clock in here.
Yeah.
When the signal leaves the satellite, eventually sometime later on, about 77 milliseconds later on, in fact, this picks it up.
Right.
Then the receiver takes a reading of its clock when the signal arrives.
Yeah.
So the signal, the receiver knows when the signal got there, and it knew when it was transmitted.
So I now know where that satellite is.
You know two things. You know where the satellite is,
and what time,
and you know how far
away it is. Okay.
Right. That's basically it.
Wow, you know what's just struck me is just quite, this fantastic infrastructure that supports all this in terms of satellites, in terms of ranging stations, in terms of big physics, in terms of big mathematics. And every time I turn one of these on in the car, I get a bit cross because it doesn't sort of work instantly. It's amazing.
So why 27 satellites in orbit? Well, actually, it takes more than one to give an accurate location. In fact, it takes 4.
Imagine these are 3 satellites. So we've got a pink satellite, a blue satellite, and a green satellite. And we know the coordinates of where they are out in space. And the ropes represent the ranges.
We know the coordinates out in space because they've got very accurate clocks, which we can measure the time it takes to beam the signal back to Earth.
That's right. So the rope represents the range.
Okay.
So let's see what would happen if we had just one satellite.
Careful of your nice shoes.
Yeah.
Ah, okay, so with one satellite, we could be anywhere on this line, basically.
Exactly. That's
so,
right.
which is not much good.
So I know my receiver could be here, or it could be here. That's using one range from one satellite.
Let's bring in another satellite then. Ah, because we've got 2 satellites where these points intersect.
That's right.
There, that's where we are.
So in 2 dimensions, that's going to be your position fix.
Yeah.
Now, of course, in reality, in space, we're trying to fix our 3 coordinates. So maybe so much along X, along Y, along Z, or eastings, northings, and height. So we need to make a measurement to a 3rd satellite. Let's do that.
So suddenly we have where these points all intersect. This is our location in 3 dimensions.
That's right. That's right.
OK, that seems pretty convincing. But where does the 4th satellite come in?
You use the 4th satellite to synchronise your little clock with the space clocks. The problem is to do with the quality of the clocks, because the clocks up on the spacecraft, they cost about $2 million each, and they're really, really good, really stable. The clock in your little GPS receiver only costs about 15 cents. And so it really doesn't keep time as well as the clocks up on the satellite.
So the Force satellite really just there to as a sort of get rid of those margins of errors, get rid of those problems you've got.
And to make sure the satellites really are where they say they are, tracking stations like this one constantly fire lasers at them as they pass overhead.
Dallas, fire that laser.
Okay, I'm going to fire the laser. Ready? So really what we've got here, we've got a giant laser pointer, if you like. On the satellite, they've kind of got reflectors like cat's eyes. You ping the laser at the cat's eyes, it bounces the laser back. We know what the speed of light is, so, so we know where it is.
This device can tell you the range within that, within, 3 or 4 millimeters.
That's unbelievable.
Yeah, it's pretty cool engineering.
Amazing. It really is. The question is, what now for the next generation of satellite navigation?